Sorry for those that are watching the replay here. It can be kind of boring for the first few minutes. I just logged on early and I don't want to pause the recording because last time I paused the recording, I forgot to hit record again. So, so you can watch me as I look at the screen getting extra examples ready. I think it's like 1:55 now. So if you want to skip forward 5 minutes, that would be good. Hey, Michael. I am not ready at all today, so I'm like, I just wanted to start the meeting early and like get the recording going in case people wanted to come in. Time.
I have a quick question.
Yeah.
Would you have any like estimate about when the test will be graded?
I have them all downloaded, and after this class, it's kind of like how much time do I have booked?
Yeah.
My family won't bother me, right? So after this class, I have a break, and then I also, I also have built-in office hours this afternoon, and so usually that's a good time to grade. So I'm hoping to get a good chunk of it out today. Yeah.
Cool.
Yeah. Yeah, I did not grade this weekend, so.
Alrighty.
But I did make the video. I haven't linked it. I did post it on YouTube if you want to go look over there.
Got it.
Okay, I'm just making a list of things to do for myself. I was going to make some 17.6 examples, but I don't need to because we never got to the 17.4 ones. So 17.4 and 5, so we'll do those today. Always gets jacked up dragging it from one monitor to the other. Yeah, we got some of the gang coming. I have the Millennium Falcon here in honor of May the 4th.
I like it.
I actually downloaded, I had a hard time choosing. I downloaded a bunch of cool ones. Let me see, we have some other good ones here. This one's good. I like that one. There's like another, is this the one I was looking at? Oh yeah, that's kind of cool, right? It's like star field. And then there's some other good. That one is good. So many good choices. I think I'm sticking with the Millennium Falcon though. This one is off because I look like I'm sitting in the middle. I need to like sit over here. Like I can be flat. Wait, I'm Chewy. I'm Chewy if I'm over there. I need to be over here so I can be Han. Yeah, I mean I can try to make some Chewy sounds. I don't know. That was really bad. All right, well, this one's better. This is good. Okay. All right, I'm sharing my screen, right? Yeah, okay. All right, schedule update here. Boy, we are in the stretch run. Stretch run now. And like we are running too. We are not messing around. So we are already, looks like I need to update my schedule here. So this week we are ostensibly supposed to watch 17.6 for today. That's a long section. There's still one video left. So we haven't done any 17.4 and 17.5 practice. So we can work on that today. We can get to some 17.6 if you have homework questions. We're gonna do one last homework assignment. It'll be 17.4 and 17.5 will be due this week. So we're gonna do just Green's theorem and then divergence and curl will be the last homework assignment. 17.6, 17.7, 17.8 will all be on the final. I will try to help you narrow down what types of questions to focus on. So I'll really try to do that, especially the last two questions, the last two sections. So actually 17.6 is the biggest one. Hopefully you've watched the first two videos. Once you get that, I think 17.7 and 17.8 are fine. They're not like super long sections. They're basically like another Green's theorem. There are two more theorems and they're kind of like Green's theorem. Hey, these two different things are equal. And that's it. We're gonna meet on Monday next week, a week from today, do last questions, do some practice if we have it, otherwise some homework questions. I'll post the final exam after class and then it'll be due the end of the day on Wednesday. We're not gonna hold class on Tuesday during that last finals week. We're getting there. Michael asked earlier about grading, when to expect that. I have my afternoon free is pretty free, so I'm hoping to do some grading. I do have like everything downloaded and I'm ready to go. I did post the video key. It's just on YouTube. I posted it in the Discord chat there too. But once I should be able to get a good start this afternoon and then hopefully get those. It'd be nice to get them back by class tomorrow. So you kind of have that. I know it's always hard to wait. And I was being very selfish and not grading this weekend. So sorry, not sorry. It was really nice out. So I think it was a good choice for my mental health. Does anyone have any questions about timeline, about how the last week and a half are gonna go here?
So just to make sure, you said that next Monday will be like our last Zoom class.
Correct.
Okay.
Yep. Anybody else?
Approximately how long is the exam going to be?
That's a good question. So that is a really good question. In a regular time, we would actually do two of them. It would be on 2 different days. If you look at our original syllabus, it has a Monday final and a Wednesday final. And so you can think of it roughly like a double test.
Okay.
Yeah. So don't wait until 10 o'clock on Wednesday. That will not end. That will not end well. That will not end well. You have
Audio is not working.
Thank you. I was like messing with the jack and I pulled it out just a tiny little bit. So you have a little bit of an advantage because it's kind of a big advantage. You can pace yourself if you want. I'm not gonna say you have to work on the exam in one continuous shot. So you can work on it. I am gonna ask you to kind of like you did for the last one, make sure you have all your studying done and you have your formula sheet down and then you're doing the exam. I don't want you to open the exam, try some stuff, then realize you need to study more and go back and study more. You know, that's not really the situation we want to be in. I would imagine in the fall, if we are still online, and it looks like we are even more so going to do that. I had a meeting. I'm on a planning committee for our division for math, science, engineering, health professions. And by the end of the meeting, the dean was like, I don't know how we could do it for math classes and other classes that really don't need a lab and don't need to be there in person. So it's looking more and more like we're going to be online, and it's going to be more planned. And my guess is you will be more likely to have a window. Exam is posted at 2 p.m. and you have until 4 p.m. to turn it in. Like that's going to probably be what will happen, at least in the math department for next fall. Some of my colleagues are having a much harder time with their classes, and there's like rampant cheating, and so there might be a situation where everybody has to have a camera on them or something like that. I don't know, maybe I'm naive, but my classes have been pretty good. So it might be different in the fall. But for us, you'll have Monday after class, it'll be posted, and then you can, if you want to chunk it out and do 2 or 3, kind of do some earlier stuff and kind of pace yourself, that's fine. But plan on, to Nathan's point, plan on roughly a double exam, because it would have been 2 days for us. It would have been split.
Okay, and that does cover from chapter 13 all the way through 17, right?
Correct.
Okay.
It is inclusive of the entire chapter. The newer stuff, there will probably be one of everything. So there'll be a Green's theorem question. There'll be something about divergence in curl. There'll be a surface integral. That's 17.6. There'll be Stokes' theorem, and then divergence theorem, but they're also surface integrals. So anyway, it's complicated, but the newer stuff will be, everything should be on there in some way or form. Obviously the earlier parts, couple from each chapter, something like that, 2 or 3 from each chapter. Yeah. That's good questions, Nathan. Any other, for our note cards? Yeah, Tyler's, that's fine, Ty. You can just use all your previous ones if you want. Yeah, that's totally fine. He was asking about note cards, for sure. If you want to make a new one to organize it better, it doesn't matter to me. It's totally fine. I think it might get a little cluttered. Maybe you could like tape them together or something, because you had like half sheets for the first couple and then like a full sheet, and and then you're gonna be like, okay, Mom and Dad, I need the whole table for the next 3 hours. No coming in here. I've got my beats on, my noise canceling. Like, I don't know, whatever works for you. But yeah, you can use your previous ones. That's fine. You gotta have new ones too. You gotta add some new stuff to it too. All right, good questions. Any other timeline, big picture grading questions? All right, I'm sure you had a little bit of post-exam letdown over the weekend and like relief, like that it was over and you didn't like do a ton, but ideally you should have started on some of the homework from 17.4 and 17.5. So that's what we would usually do next, is see if you had any homework questions. So, do you have any homework questions? I can pull it up here. All right, 17.4, Green's theorem question, parts 15, numbers C and D from Michael. All right. I do not have the homework up yet. It's loading right now. Slowly. Come on. All right, there we go. Green's theorem. So this is the kind of thing, by the way, even in this chapter, you know, I don't know if this sounds familiar. Hopefully there's two different forms for the Green's theorem. We're probably not going to have both on the final. It's just too much. So we'll have one of them on the final. All right, so we're looking at 15. Oh, it's getting started. 15, C and D. Yeah, that's the meat of the, that's the meat of the problem there. We should get Green's theorem in here too. So as soon as I get this, what happened to my, oh, that's so weird. All right, so there's that. Let's get Green's theorem. Let's get both forms of Green's theorem in here. So let's go over to the notes, remind ourselves what those are. We have the circulation form is that the circulation around the curve is equal to the double integral of the curl. And it's not what I wanted to go back to. All right, so version 1, the circulation equals the double integral over the region of the curl. That's the circulation, and then this part in here is the curl. Okay, so that's the circulation form, and then we have the flux form. Make sure I get that. Why do I keep trying to change what I'm missing? This is annoying. It's just over here. So then a couple pages down, we'll have the flux form. All right, so circulation F dot N ds equals, and then that's the double integral of the divergence. And that's where you add partial derivative of F with respect to X and the partial derivative of G with respect to Y. Oh, I'm in the wrong tab, that's what, okay. Equals double integral over the region of fx plus gy dA. This is the flux, so that's if you have a path, it's how much of the field is pointing, it's going out normal to it. That's why the n. And then that's the double integral of the divergence. So flux form and circulation form, those are both Green's theorem. I need to get this and organize my stuff here. Maybe we did do 17.4, but no. So Michael, you said you got A and B okay? We're just focused.
Yeah, like the parameterization I think I got, but maybe we could go over that too.
Maybe, yeah, just to make sure, because we don't really want to do the line integral unless we have the right parameterization.
Oh wait, no, because we did that on Thursday, so I have that. I was just thinking about the one for 16, but that's a homework question.
You can ask about that, that's fine.
So it's like
let me get over there. So are you wondering about the parameterization of it, or?
Yeah.
Like
for the so for R1 I put t and then 2t squared minus 2t, and for R2 I just put 1 minus t and 0.
Hold on, sorry, I'm like wasting all this time technology here. All right, so say those again. You said R1
t and then 2t squared minus 2t.
Okay.
For C2, I put 1 minus t, 0.
And let's see here. So this would intersect at 1, right? Just making sure what that point is. And so, yeah, so this one you can just, so for R1, that's got the orientation going in that direction, you can just pick x is t, and then y is equal to whatever the function of t is. I feel like I need to zoom in a little bit more here, my apologies. I feel like it's Monday and I'm like relearning everything again. Just put this down below. So I'm okay with it. I'm on board with that. What is happening? Yeah, that makes sense to me. Again, this is y equals 2x squared minus 2x. And so if you have that orientation from left to right, then you can simply do the x value is t and the y value is whatever the function is of x. And then to make it go backwards, you can, we did this before, that 1 minus, I think we did a 2 minus example, if I recall, but this is at the point 1, 0. So when t is 0, it's out at 1, 0. When t is 1, it's back at the origin. That's how you get it to go backwards, is that 1 minus t. So yeah, those look good to me. Did you want to do the Green's theorem, or were you more focused on the parameterization to make sure you had the right parameterization?
Well, like I did the line integral, but like when I used Green's theorem, I'm getting confused about those.
Because the one good thing here is when you do the line integral, actually be 2 of them because you have 2 different paths, you should get the same thing as the double integral when you're done.
Yeah, and I didn't, so I don't know where
That's
I'm
not a
going
good
wrong.
sign, right?
Yeah.
Right. Let's see your Green's theorem, or let's see because that one's a little bit easier in my opinion. Fx plus gy dA. So my field here, let's see, partial derivative of f. The field is x1. That's simple. So the partial derivative of f with respect to x is 1. The partial derivative of g with respect to y is 0. So we're just, all we're doing is finding the area then. And I would,
so I had it going from 2x squared minus 2x to 0, and then from 0 to 1.
0 to 1. Yeah, that's a pretty easy double integral. Once you get it like laid out, you get everything set up right. So I think everything looks good to me here. That'll be y from 2x squared minus 2x to 0 dx, which will actually just make it 0 minus that. So it'll just be negative 2x squared plus 2x dx. Negative 2/3 x cubed plus x squared from 0 to 1. So negative, so it looks like 1/3. Does that look right?
Yeah, that's what I got. Just I didn't get that for the line integral.
Line integrals. So how about we'll do this compromise. Let's set up the line integrals, both of them, and see if we have the setup right. If we know the setup's right, they're just calc 1 integrals. So there's some small error in there somewhere that went wrong, and I'll let you kind of investigate that. But let's set them up together. So this is the right side of the flux form. I find the flux form more challenging for me because it's easier for me to do the circulation form because it's just f and then the dot product with r prime dt. And I have to go back to the notes actually even now to remind myself how to do that flux form. So let's write it down here. The general one, I'm going to go back to the 17.4 notes. So this is what we need to do now. Let's go back to the 17.4 notes. And there should be a couple of, or not 17.4, the flux integrals. Where did that go? 17. Yeah, so you have to do, see, there's a lot more work here. You have to do t cross k, the tangent vector cross with k for each one of those. That's your n vector. I feel like there is a shorter version here too that we're missing. Let me just write that down. And then ds is the magnitude of r prime of t dt. If we just grind this out for the first one, r1 is t, 2t squared minus 2t. Incidentally, part of the reason why they're having you do this homework question is to see the value of Green's theorem. Because the double integral was pretty easy. I mean, there's 6 steps there, right? So amount of labor, relatively minimal amount of labor.
Yeah.
This will be much more than 6 steps.
Yeah, I don't know what like k, like what's the k vector?
0, 0, 1. It's the unit vector.
Oh, okay, so it's crossed with the unit.
So
K is like a
Daniel,
unit, right?
what am I missing here, Daniel? Because that's why I'm like, I knew there was another version somewhere. Yeah, you could use a lot. Yep, you could do it that way. They're equivalent. Yep. So I knew there was, I'm like, wait a minute, there's got to be a simpler way to do this. I just kind of off my rhythm today. So the two forms, they have 3 versions really. The circulation form has the line integral with the field .dr, and then it also has this like differential version, which is still a line integral, but it's the differential version. And then it has the Green's theorem, the double integral of the curl. And you're right, Daniel, the flux form, the flux is similar. It has the line integral of the flux to get the flux, but it also has this differential form here. And then it has the double integral of the divergence. So that sounds a little bit better, a little more manageable.
Wouldn't that be like integrating 0 though for the problem? Because it's like
maybe it's possible that that one is 0. So we're going to do f dy minus g dx. Is that right? F dy minus g dx. Yep. Let me erase some of this other stuff here. So for this first one, this actually isn't a closed one. This is over C1. And f is x1. That's f and g. And then we have our path, r1, is t, 2t squared minus 2t. So our dx will be 1 dt, and dy will be 4t minus 2 dt. So we have 1 dt minus 2t squared minus 2t dt. And so we're basically, right, it's 2 separate integrals. We can combine them together. And then we need, I guess we need the bounds. I'm sure you had that in mind. Michael, I don't think I didn't write them down at least before. Did you have those written down for your the two paths, Michael?
Yeah, I think it's just 0 to 1.
For both of them, right?
Yeah.
Yep. Yep. I agree.
But so back to the integral, wouldn't it be 1 dt minus then,
Oh, I didn't take the derivative.
yeah.
I took the derivative below, but then didn't write it in there. 4t minus 2. Yeah. Mm-hmm. All right. 3 minus 4t. Yeah, I feel like my brain is turning to mush. I did the exam in preparation to make sure all the problems were doable and all that. So I did the whole exam and then it made my video key. And I didn't really have my previous version open when I did the video key. And it turns out at the end, there were 3 problems that were different. And I was like, oh no, do I have to redo the video? Well, actually, no, the first version that I had just made as practice, there were 3 problems that I did wrong. Like I made like little errors on them. And the video key, I'm pretty sure is right. Like I feel like I'm just mush lately. All right, so now I kind of want to keep doing this one because I'm losing confidence. I want to see, do we get the 1/3? Like now I'm kind of interested. Can we get the 2 sides to be equal? So 3t minus 2t squared from 0 to 1, which will be 3 minus 2. So that first one gets us 1. Okay. Now the other one is going backwards, like it's going against the field, right? The field is x1. And so the field is kind of like, it's got a y component of 1, it's got an x component, so it's going like this way, right? Actually, it doesn't, it's got a 1. So it's that second curve is working against it, so it should be negative. And I'm saying that because we got 1/3 for our double integral, and we just got 1 for the first curve. And so the second one better be negative because we have to subtract 2/3. Hopefully we get negative 2/3 for the second one because that's what it should be. Let's try the second one. We said 0 to 1 again, but I have to write the second curve now. R2 was 1 minus t and 0. All right, so we need oh no. Shoot. I made a mistake. Going back to the previous integral, do you see the 1 dt and the 4t minus 2 dt?
Yeah.
What did those represent?
Like the parameterization of the C1 curve.
Kind of like, oh gosh. Can we like rewind 20 minutes? So I was trying to use this formula here, but I didn't. I did not actually use it. I need f dy, where f is from the field. And then I use dx for some reason. So we need to go all the way back here. I am sorry. So f is the x of the path, right? F is x. And so that's t. And then dy is 4t minus 2 dt minus g from the field is 1. And then dx is 1 dt. That's f dy minus g dx. Let's try this again. 4t squared minus 2t. Now we're going to get our thirds. Minus 1 dt. So that's 4/3 t cubed minus t squared minus t from 0 to 1. Oh, now this one ends up being negative. What? 4/3 minus 1 minus 1. So negative 2/3. So hopefully maybe the other one will end up being positive 1. I don't know. I guess it's possible. It's flux, not circulation. So it's not that we're moving against it. It's how much of it is moving like perpendicular to our path. It's flux, not circulation. I think this looks a little bit better. Okay, let's try the second one now. Again, the field F is x comma 1, where x is F. So we need, let me write it up above again. We need F dy minus g dx. That's what we need up here. So F from the field is x. So that's 1 minus t. dy is just 0, because y is already 0. Okay. Minus g from the field is 1. And then dx is going to be negative 1 dt. Somehow, miraculously, after all that, this is going to get the right answer. Don't ask me how. Because this is just the integral from 0 to 1 of dt, which is t from 0 to 1, which is 1. And so if you add the two together, I'm just trying to be clear here, the closed integral of to find the flux is the sum of the two line integrals. And we got negative 2/3 plus 1 is 1/3. Oh, man. I made that too difficult. First, thank you, Daniel, for the suggestion. That was definitely helpful. We need to have good notes when we're getting ready for this test. So make sure when you are making your notes that you have all three versions for Green's theorem. And we needed to use the middle version here. That was the easiest one. I will sometimes, for the circulation one, you've seen me, for the circulation one, you've seen me do the one, the f dot dr. You've seen me do that one. That one, I think, that dot product is manageable. We haven't done the differential version very often. But for the flux, that first integral is more challenging. It's often easier to use the differential version. And so that was a good catch on that one, Daniel. And then second is, I don't know why, I just went like way too quickly. And I kind of lost what was F, what was dy. I wasn't really even using the formula, and that's kind of how I went off there at the beginning. So it's like really careful attention to detail on these integrals. But we got it to work. We got the same answer. And I like your point, Michael, is like, well, I did it all, but I know it's not right because I wasn't getting the same for the two versions. And that's the whole point of the theorem, is you should get the same thing. So, That was good recognition of that.
Got it.
What we have found, by the way, is that over this region, there's a net outward flux across that path. There's a net outward flux. I don't know if that's a little or a lot. We don't know what the scale is here, what these numbers are, but you know, it's 1/3 of whatever the units are. Whew. All right. That's a good one though. That was a good example. I don't think we had done in our notes where we didn't do one of those. I only did the circulation ones. So this was a good one for us to do. Any other homework questions? We still have the homework up here. If anybody has any additional questions from 17.4. That's what it is. I didn't have my coffee. Yes. Figured it out. Any 17.5 questions? The divergence and curl. Very quiet. I think what we should probably do then for the rest of our time, let's see what we have done and what, let's see, this was, we were practicing for the exam. So let me pull this down here. Let's see where we had done here. We had talked a little bit about, yeah, see, so we did Green's theorem. We did an example that was the circulation form. And we talked about how like that line integral was a lot of work and the area was much easier using the double integral of the area. So here's the flux form, and this one, it would have been good if we had gotten to this one. That probably would have helped help us do better on that homework question. So let's do another one. This will be another good practice with the flux form. We have a region and we have a field. Compute the two-dimensional divergence, evaluate both integrals in Green's theorem, and check for consistency. So again, check and make sure they're equal. Oh, the region is nice. So at least the region's just a single curve. And it's just inside the unit circle. You have to be a little careful with the unit circle. There are many ways to parameterize the unit circle. Do you remember, I feel like this came up, something has to be true about our path in order for Green's theorem to apply. Do you know what that is?
Be counterclockwise.
Yes. Now, if you did not notice that and just said, well, I'm just going to use R of t equals unit circle, cosine t sine t. Well, you'd be fine, because that's the orientation that the unit circle actually is. So, but you just have to be careful. You do need to be careful. Sometimes you can be given a path, like they just switch them around on you, and they just give you sine t, cosine t. And you're looking at that and you're like, oh, well, that's the unit circle. It just goes a different order. And then you do your answer and your answer is negative because it goes backwards. So it's just something to keep in mind. Whatever path you choose here, this path must be counterclockwise. And it already is, so we don't need to modify it, but it's something to be cognizant of, and make a note of that. When you do these theorems, don't make a note just of the results, like what the formula is. Make sure you're noting what has to be true, the conditions for the theorem. So the flux form, the region has to be simply connected. The boundary has to be piecewise smooth, so no gaps in it. And then it has to be oriented counterclockwise. So that's something to keep in mind there, to make a note of that. All right, so back over here. Compute the two-dimensional divergence. the divergence should be, I always want to, let me just double check here. So the divergence should be just the sum of the two partial derivatives. So the partial derivative of f with respect to x plus the partial derivative of g with respect to y. That's the divergence. It's partial derivative of f with respect to x plus the partial derivative of g with respect to y. That's from our field. Okay, partial derivative of f. F is x squared plus y squared, so the partial derivative with respect to x will be 2x. And then the partial derivative of g with respect to y, well, g is 0, so that'll just be 0. So the two-dimensional divergence is 2x. All right, let's compute both integrals in Green's theorem. I'm going to write all three versions, but really it's, let me make sure, I'm going to double, yeah, that's right, right? No, double check here. We just did this one. So let's make sure, f dy minus g dx. Yep. F dy minus g dx, okay? That's the same, that's to calculate the flux. And then Green's theorem says this should be the same as the double integral over the region of the divergence. Partial derivative of f with respect to x plus the partial derivative of g with respect to y dA. Okay, well let's do the one that was harder for us last time first. Let's do the flux. Integral over the curve of f. What is happening? Whoa, there's like this lag. Hold on, I have a child talking to me here. Okay, I'm gonna do classic teacher move. Why don't you try to set up the integral while I go talk to my child who's been playing Xbox for 3 hours when he knew he was only supposed to have an hour. So see if you can set up, you should just have one integral here because it's a single curve. So see if you can set up, use the middle form here. Use that middle form and see if you can get a nice Calc 1 integral dt. I'll be right back. All right. This is fun. I like teaching while I have children in the house. It's great. It's great. Okay, so let's see here. We have our field. We'll see how you did. We have our, I'm going to copy the field again. It is x squared plus y squared comma 0. So again, the x squared plus y squared is f, and the 0 is g. So we have f dy actually, let me just, there we go. So we have f is x squared plus y squared. And then dy is cosine t dt from our curve. And then plus, or no, minus g dx. Well, that's convenient. G is 0. And then it doesn't really matter what dx is. And then dx is, I guess, doesn't really matter, negative sine t dt. Almost. We need some t intervals, right? I guess I don't really need a closed integral. This is just a dt. So what would we put for t? Did anyone have that?
Zero to 2 pi.
Yeah, we need our complete circle, 0 to 2 pi. Oh, this is better than it looks. I was like, oh no, we have to substitute in x squared and y squared. But they're cosine and sine. So you get cosine squared plus sine squared times cosine t dt. Now, all you get is the integral of cosine t dt. Anybody have that?
Yep.
Yeah. Nice. Cool. Wonder if the double integral will be harder this time. I don't know, maybe they'll both be the same. So that's just sine t. Oh, this is not interesting. From 0 to 2 pi, and so we get 0. Interesting. So there's no flux. There's no outward flux across that path. Oh. Yeah, okay. I think that makes sense. Because there's no net outward flux. Because the flux on that path, the field, excuse me, the field on that path, the field is just the vector 1, 0. Because on that path, x squared plus y squared is always 1 on that path. So on that path, the vectors are all a length of 1 to the right. And so on the left, there's a little negative flux that's coming in, but on the right, there's exactly the same amount of flux outward. So the net flux over that path is 0. So that's plausible to me. I don't know if that makes sense to you. So that, I think that's good. So now let's try the double integral over the region of the divergence. What was the divergence? 2x. And then, oh, I don't want to do this. Because it would be, I mean, I don't want to do x and y here. Because then I have to do like top half of a circle, bottom half of a circle. Right, here's my region. Circle radius 1. Any ideas how we could do that without doing like the whole square root thing and, you know, negative square root of this to positive square root of this for the double integral? Yes, it's a circle. It's a circle. Use polar. Michael is right. Use polar. 2r cosine theta. Oops, not r cosine theta. R is 1. Right. X is equal to r cosine theta. So for r's, x will be 1 times cosine theta. So 2 cosine theta r dr d theta. R goes from 0 to 1, and theta goes from 0 to 2 pi. And so we just get, watch this, we get the integral from 0 to 2 pi cosine theta. When I integrate 2r dr, I get r squared from 0 to 1 d theta, and I get the integral from 0 to 2 pi of cosine theta d theta, which again is 0. That's the same integral we did above. Maybe I should have put this one in the homework instead of 16. Maybe I should have been paying more attention. 16 probably wouldn't have been as hard if I had been paying more attention, but this is definitely easier. In my opinion, what makes this one easier, the primary thing is the path, because it was a single path, so we didn't have to split the line integral up into two integrals, and the path was a circle, the unit circle. Like traveling around the unit circle is easy. Integrating on that, a line integral on the unit circle is nice. Plus the field was x squared plus y squared as the x component, but on the unit circle, that's 1. So this one was made easier by a lot of stuff. All right, any questions on this? This happens to be number 30 from the homework, but any questions on the two forms from the flux form of Green's theorem?
Yeah, I do.
Mhm.
How do we know when to use like the circulation and then the flux form for like Green's theorem?
Yeah, it just depends on what's asked. You'd have to be told, you'd be told find the circulation or find the flux.
Oh, okay.
Yeah. Here they're telling you use this form of it, but from a practical perspective, well, I want to know like how much water is flowing out across this. Like imagine you have a pipe from the ground that has a circular thing, and you have some kind of function for the field of the water flowing over it. And so you might wonder what's the net flow of water over that. And so, well, that's flux, that's outward flux, how much is flowing out there. Another one you might wonder, some kind of electromagnetic circulation, some type, the problem would tell you, you'd have to know which one. It would
So
be,
seeing in the homework, because it's like, it'll ask for like curl or divergence for like one of the steps. So is that kind of like an indicator of what form you would use?
It is, but it really wouldn't be there. The question I'm going to ask is, I guess I get your point, how like if you ignored the heading for the problem and just read it, if you read part B, evaluate both integrals, well then you're like, well, which form do I use? And to your point, oh, because it said divergence, I know it's that form. For our exam, we'd be very specific. I'm trying to remember exactly what I asked last time, how I asked it. I don't have it handy right now, but we'll try not that will not be the challenging part of the problem. We'll try to make that very clear, whether we're looking for the circulation or the flux.
Got it.
All right. Any other questions on this one? All right, let's see what else we have here. Right, yeah, you see how this one is just saying compute the circulation on and the outward flux across this boundary. So I think we're gonna try to make a guess. It's not telling us which one to use here. Which like it doesn't say prove that Green's theorem, like verify Green's theorem. So I think we're gonna try to be wise and choose, do I want to do the circulation or do I want to do the double integral of the curl? Or do I want to compute the flux as a line integral, or do I want to compute the double integral of the divergence? So let's do circulation. So circulation again is the line integral f dot dr or the double integral over the region of the curl dA, and that curl was the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And I always want to double check there, make sure I got that right. So let me just jump over quick here. Good, okay. So let's practice setting up both of the integrals, and we'll see how much time we have left then. It's already 2:55, so we'll see. Okay, well, let me recopy my f. That is, oh, man, that does not look fun. Taking the dot product of, I think I already know which one I want to do. I have to take the dot product of that with dr. Okay, so r is, oh yeah, okay. I think this is pretty clear. I'm not going to set up the circulation on this one. Okay, so it's the 8th annulus, which sounds weird, but r goes from 1 to 2, theta goes from 0 to pi over 4. So all this is 1, 2, that, okay, pi over 4. So this is, I don't know if this is obvious to you. This is obvious to me that I'm not going to do the line integral. Can anyone summarize quickly one quick reason why we would not do the line integral to find the circulation? Complete this sentence. The line integral is a bad, nope, terrible idea because what do you think? I'm with Daniel on this one. He typed in the chat, there are 4 curves. Yeah, that's the #1 reason. 4 curves. And not only that, you're going to integrate f dot dr. I mean, some of the r primes might be okay. I don't know, but you're going to have to integrate the natural log of x squared plus y squared in there somewhere. And you're going to have to integrate inverse tangent of y over x. I'll pass. Thank you, but no thank you. So let's try the other one. Let's see what that looks like. Double integral, partial derivative of g with respect to x. Okay, 1 over 1 plus y over x squared. And it's with respect to x, so we need to take the derivative of y over x. That's y x to the negative first, so negative y over x squared. That was the derivative of g with respect to x. That's the derivative of, this is the partial derivative with respect to x of the inverse tangent of y over x. That's the g. And then I need minus the partial derivative of f with respect to y. So that's 1 over x squared plus y squared times 2y. And then that's all dA. Well, this looks bad. I think it will not be that bad, but it looks a little rough right now. I'll put, that's the over the region R. It actually simplifies reasonably nicely because you have negative y, and then when you distribute the x squared into the denominator, you get x squared plus y squared, but then you have another 2y over x squared plus y squared. That's a double integral over the region. And so it actually is not that bad. Negative 3y over x squared plus y squared dA. I'm with you, Ty. Ty's thinking polar. I am thinking polar as well, especially when you look at the region. It's like a little sector. What do they call it? An annulus? Eighth annulus? I think an annulus is like a washer. So this is an eighth of a washer. So I agree. I was going to take a little break though right now. Does anyone have any questions about how I got to this point? Okay, not seeing any. All right, let's look at the region. I agree. Let's try switching to polar. So that's what, negative 3r sine theta over r squared. Let me just write it as r cosine theta. Actually, we don't need to do that. We know x squared plus y squared is r squared. That's fine. We can just do that. And then r dr, r dr d theta. That's awesome. R goes from 1 to 2, and theta goes from 0 to pi over 4. Can you imagine setting up that region in x and y? Not good. Not good. Definitely polar. This started out rough, but now it's just negative 3 sine theta. Dr d theta. You lose all the r's in the integrand. Doesn't get much better than that. So I'm just integrating essentially over a rectangle now. So you can integrate either one first, it doesn't matter. Negative 3 sine theta from, and then it would be r from 1 to 2 d theta. So there's, that's just 1. So it's just integral from 0 to pi over 2 of negative 3 sine theta d theta, which would be 3 cosine theta from 0 to pi over 2. Cosine of pi over 2 is 0, and so we get negative 3. Okay. I don't know if it's right.
0 to pi over 4?
Oh, pi over 4? It was just, I did a quarter annulus, didn't I? Zero to pi over 4, 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 pi over 4. Change all my pi over 2's to pi over 4. Let's see here. So that's 3 times square root of 2 over 2 minus 1. Still negative. I don't know why it's negative. I don't know. The field's kind of weird. It's hard to just look at that field. It's hard to just look at that field and kind of see, oh yeah, that's going to be a negative number. I don't know. You could use Maple or something to graph it, a field plotter to graph it and take a look at it and see if it looks like on your path, are you going to get a negative circulation? But my guess is it's probably this, because this is such a weird path, it's probably going to be really hard to see that it's a negative circulation. That's probably going to be really hard. So that one is a nice example of the value of Green's theorem. And I feel like it's like there was a question on the test There's a couple of them where you really, if you were really flexible with different versions of double or triple integrals, you could manage the problem. And if you weren't flexible, oh, it says circulation, I need to do the circulation thing. And I need to do a line integral of f dot dr, and that's all you knew how to do, you could get stuck. Whereas this one, if we know, well, it says circulation, so I should be able to use either form. It's a closed region. The path goes in that direction. So maybe I can use Green's theorem. Let me set up both of them to see where it leads. And really quickly we saw, hold on, this would be 4 different paths. I do not want to do the circulation and compute that directly. Instead, let me do the double integral of the curl. And that was more manageable. Okay, I think that is it for today. Any last questions on this last example from today? Okay, all right, that will end today's class then. And you're working on 17.4 and 17.5, those two. If you haven't watched the 17.6 videos, there are 2 of them currently posted, and you should watch at least those 2 for tomorrow. And I'll work on getting that 3rd one up later today. So try to watch those surface integral questions for tomorrow, so we can make sure we have time tomorrow to talk about those tomorrow and Thursday. All right, that's it for today. Enjoy the rest of your Monday afternoon.